Hi, this is Dr. Jivikas Paul. In this session, we are going to discuss about the conjugate beam method for the deflection of beams. The slope and deflection of beams and cantilever may be obtained from various methods. So, the slopes and deflection for simply supported and cantilever beams may be obtained from various methods like double integration method, moment area method, Michaelis method, etc. But these methods become laborious when applied to the beams whose flexural rigidity, that is EI value, is not uniform throughout the length of the beam. That means these methods, double integration method, Michaelis method, moment area method, so double integration method, mainly double integration method and Michaelis method are used only for uniform EI values, not for the EI value, different EI values. Okay, so this method is suitable. Conjugate beam method is suitable for the beams having different I values. So throughout the length of the beam, the slopes and deflections of beams can be easily obtained by conjugate beam method. So in conjugate beam method, what is conjugate beam method? It is an imaginary beam of length equal to that of the original beam, but for which the load diagram is M by EA. That is, the load at any point on the conjugate beam is equal to the bending moment at that point divided by EA. So what is it? It is an imaginary beam. The length of this imaginary beam is equal to the original beam. Length will be equal, but the load diagram will be, so for the given beam, original beam, if we draw the M by EA diagram, that M by EA diagram will be the shape of the conjugate beam and it will be the load. We will come to know clearly about this. The slope and deflection at any section of a beam by conjugate beam method is given by, first one, the slope at any section of the given beam is equal to the shear force at the corresponding section of the conjugate beam. So slope in the original beam is equal to the shear force in the conjugate beam. And the deflection in the original beam is equal to the bending moment in the corresponding section in the conjugate beam. The deflection at any point for the given beam is equal to the bending moment at the corresponding section of the conjugate beam. So the slope in original beam is equal to the shear force in the conjugate beam at that particular section, and deflection in the original beam is equal to the bending moment at the in the conjugate beam at that particular section. So let us see the relation between actual beam, original beam and conjugate beam. So actual beam, first point is, if it is simply supported in the actual beam, in conjugate beam also it is simply supported. Free end, if it is free end in say actual beam, it will become fixed end in conjugate beam at that section. If it is fixed end, then in conjugate beam it will be free end. Slope at any section, here it is shear force at the corresponding section. Deflection at any section is equal to bending moment at corresponding section. So a given system of loading is M by IA diagram in the conjugate beam. So if the bending moment is positive, that is sagging, then M by EI load diagram is positive, that is towards downwards. If it is hogging, it is towards upwards. Load is towards upwards. Let us discuss the first case, deflection and slope and deflection of a simply supported beam with point load at center. So here is a simply supported beam with point load at center, L by 2, that is spans AC and CB. And you can see the bending moment diagram there, WL by 4 is the maximum bending moment diagram. So here I values are same for AC and CB. Therefore, bending moment diagram is equal to M by EA diagram. Okay. Next, coming to conjugate beam, the shape of the conjugate beam will be same as the M by A diagram. Here M by A diagram shape and bending moment diagram is same. Therefore, bending moment diagram shape will be the shape of a conjugate beam. And coming to the supports, in first diagram in actual beam, at A it is simply supported, at B it is simply supported. Therefore, in conjugate beam also it will be simply supported at A and simply supported at B. And as the bending is sagging, so sagging between A and B, so it is positive bending moment. Therefore, the load is downwards in the conjugate beam. The diagram shows a simply supported beam of AB of length L carrying a point load W at the center. See, the bending moment is shown in the figure. The bending moment at A and B is 0. The bending moment at the center is WL by 4. The conjugate beam AB is shown in the figure C. The load of the conjugate beam will be obtained by dividing bending moment at that point divided by EI. The shape of the loading on the conjugate beam will be same as the M by A diagram or a bending moment diagram, because here I values are same for AC and CB. So the ordinate of loading at C on conjugate beam is equal to WL by 4EI. So let R and RB be the reactions of A and B for the conjugate beam, and total load on conjugate beam is equal to the area of load diagram, that is M by EA diagram, area of load diagram on the conjugate beam. So area of load is half into AB into CD in the conjugate beam. So AB is L, CD is WL by 4EI. WL by 4EI, because M by EI diagram will be the shape of conjugate beam. So WL by 4EI. So it will become WL square by 8A. So the reactions at each support for the conjugate beam will be half of the total load. So total load is WL square by 80A. So half RA RB means WL square by 16A. So if theta A is a slope at A for the real beam, the YC is the deflection at C for the real beam. So according to the conjugate beam, theta A is equal to shear force at theta A in original beam, real beam, is equal to shear force at A in the conjugate beam, and deflection at C in the original beam is equal to bending moment in the bending moment at C in the conjugate beam. So theta A is equal to R, shear force means RA, is equal to WL square by 16EI. So to find deflection at C in real beam is equal to bending moment at C for in the conjugate beam. So Y equal to YC equal to bending moment at C. So bending moment at C in conjugate beam is equal to RA into L by 2 minus half into L by 2 into WL by 4EI into central distance half into L by 3. So YC equal to WL square by 16EI into L by 2 minus this. So YC will get as WL cube by 48EI. Let us discuss the other case, deflection and slope of a cantilever with a point load at free end. So here is a cantilever beam with point load W at free end. AB length is L. So bending moment diagram is WL, you can see here. So in conjugate beam, as it is only one span here, only one I value is there. Therefore, M by EA diagram and bending moment diagram will be same, but will be same. So the shape here in conjugate beam will be the same, but it will become WL by EI. Load will become WL by EI. So here it is load will be upwards. So why in conjugate beam? Why because in the first diagram real beam the deflection is towards downwards. So bending moment will be a hogging. So negative bending moment. So in a conjugate beam it is upwards. The diagram shows a cantilever beam AB of length L and carrying a point load W at the free end. At B, the bending moment is 0 at the free end and the bending moment at A is equal to WL. The bending moment is shown in the figure. The conjugate beam can be drawn by dividing this bending moment at any section by EI. The loading on the beam will be negative, that is upwards. At bending moment for cantilever is negative. The bending moment on conjugate beam is above. So theta B, slope at B, is equal to shear force at B in the conjugate beam. Slope at B in the original beam is equal to shear force at B in the conjugate beam, and deflection at B in the original beam is equal to bending moment at B in the conjugate beam. So theta B equal to shear force at B for conjugate beam equal to load B star, A star and C star. So half into AB into AC, half into L into WL by A. So it will become WL square by 2A. So YB equal to bending moment at B star for conjugate beam. Therefore load B star, A star, C star into distance of center of gravity from B. So half into L into WL by EI into X bar, that is 2 by 3L, that is YC equal to YB is equal to WL cube by 3EI.